We want to be able to predict the weight of giant pumpkins. So when growing a giant pumpkin for a competition, the growers need to keep track of the weights. And so it's difficult to weigh large pumpkins after a while because you don't want to ruin them. So the growers measure around the pumpkin, both horizontally and vertically, and then they add the results. This is called the OTT. It's called over the top measurement, and they use it to predict the weight of the pumpkin. So OTT is measured in inches, and then the actual weight of the pumpkin during the competition when they pick them up and they measure them, those are measured in pounds. And so here what we have is we have the first 20 of the official competitions in 2018. And you can see, again, we have two columns. We have 10 in each column where you have the OTT inches corresponding to the weight of the pumpkins. We want to be able to enter this paired data into our calculators. Now, for whatever rhyme or reason, I entered mine into L3 and 4. Whichever one you entered yours into, just make note of that. So for mine, my OTT weight is L3. My weight in pounds is in L4. I'll need to find my least squares regression line. So when I'm on my linear regression a plus bx, instead of L1 and L2, which is the default, I'm going to have to change this to L3 and 4 for myself. So you'll notice I have to hit second and 3 and second and 4. We're going to get some fairly large values here, and we're going to need to round our values for a and b to 4 decimals. This means my linear regression equation, or my least squares regression equation, is going to be y hat. And then I have a lot of numbers for my a and b times x. And my value for my y hat, which is my predicting value, the unit on my y hat is the same as my unit for my y, which is my weight in pounds. Now I don't have much space up there in part A, so I'm going to use this space down here to be able to denote the calculator feature I used to create that equation. So I'm using the linreg a plus bx feature. I then need to identify what is in my x list. This is the pumpkin OTT measurement in inches. And in the y list, this is a pumpkin's weight in pounds. Remember, it's important that you describe accurately what these are and not just write the OTT and the weight. Because to somebody reading this, they have no idea what OTT and weight represents. You need to let them know it is of pumpkins specifically. Next, we can create our scatter plot. When you go into the plot, again, you need to remember to identify your x and your y list. If you're always in the habit of keeping your x's in L1 and your y's in L2, you'll never have to change these, but since mine are in L3 and L4, I'm going to have to do that. Plotting my points, it looks like this is in a linear relationship. They're kind of spread out apart. It still goes from left to right in an uphill manner. I would say there's a positive linear correlation, but not super strong because of how the data is so spread out from each other. For part C, it wants to know what the linear coefficient is, or the correlation of coefficient. And that's back when we did the linear regression equation. Our value for R is 0.761. Remember that a value that gets closer to 1 is considered very strong, and a value that gets closer to 0 is very weak. So 7 is, it's kind of, it's there. It's more on the positive side, but it's not super strong. We want to know now, is it possible to interpret the y-intercept? And if not, or even if, you want to explain. The y-intercept is the value at which we cross the y-axis. It's also what we consider our b sub 0. If you look at your linear regression equation, that is the value of negative 1.770. This would be also the value of our initial starting position, or when we have a weight that corresponds to an OTT of 0. So if I have an OTT measurement of 0 inches, this would mean that I have a weight of negative 1,777 pounds. That's an impossible value to have. So it's not possible for us to interpret a y-intercept because it's impossible for us to have a negative weight. So we would just say no and give some sort of explanation as to why. This doesn't have to be very specific. I'm not looking for specific language. I want to just hear your interpretation, and you just give me some sort of reasons that would make mathematical sense. Next, I want to know if you can predict the weight of a pumpkin whose OTT is 460 inches. So looking along our x values or OTT inches, you need to see if 460 falls within the range of our data that is there. So as long as 460 is somewhere within that value, then you can do that. And it is. So I can predict y hat where my x input is 460 inches. Meaning I would substitute 460 in for the value of x and perform the operations in my linear regression equation. Notice I end up with a decimal. For my current y values, they are rounded to the nearest tenths place. So I'll need to do the same thing for my y value for the predicted value, which means I will round this also to the nearest tenths place at 0.8. So a pumpkin whose over-the-top measurement is 460 inches would have an approximate weight of 2,161.8 pounds. Finally, we're asked to predict the weight of an OTT of 430 inches. Notice that 430 inches is outside of the range of values we have for the pumpkins here. In fact, the smallest value we have is 436. So because 430 is outside that range, I am not able to predict the weight of that pumpkin. So we would say no. 430 inches is outside that range of x values, so we cannot predict the y value, which is the weight.